Here we're going to talk about acid-base equations. Electrolytic solutions are those that conduct electricity because the substance dissolves in water to produce ions. When ionic compounds dissolve to produce new ions, the process is called dissociation. Dissociation of ionic compounds occurs when water molecules separate the ionic crystal into positive and negative ions. Water molecules that surround the positive cations and negative anions, this is called hydration. Here are some examples of dissociation equations. So we have salt as a solid dissociating into a positive sodium ion and a negative chloride ion. We also have sodium sulfate dissolving into sodium plus a sulfate ion. We have ammonium phosphate dissolving into ammonia and phosphate. We have potassium hydroxide dissolving into a potassium and a hydroxide ion. And we have magnesium hydroxide dissolving or dissociating into magnesium and a hydroxide ion. When writing dissociation equations, remember that the charges must be included and everything needs to be balanced. An ion, such as the sodium ion, is not the same as the sodium atom Na. So this is not the same as this. They are different. So that's why you have to be sure to write the charges for all ions and refer to a table of ions when you need to. When molecular compounds dissolve in water to produce ions, the process is typically called ionization. Recall that molecular compounds are held together by covalent bonds and ionic compounds are held together by ionic bonds. While most molecular compounds do not undergo ionization, acids are an exception. Acids produce hydrogen ions in solution, and the following are some examples. So hydrochloric acid, even as a gas, would give you a positive hydrogen ion and a negative chlorine ion. Then we have sulfuric acid as a gas would give us hydrogen and a sulfate ion. Note that we have to put the 2 with the hydrogen because there is a 2 in the sulfuric acid molecular formula. And then we have acetic acid, and it gives us a hydrogen ion plus an acetate ion as well. Now, the reason for the double arrow in the last equation will be discussed in an example in just a little while. The reactions shown above are simplified versions of what really happens. The hydrogen ion bonds to a water molecule to form the hydronium ion, H3O+. As a result, we can also write these equations the following way. And so we could write it as hydrochloric acid plus water gives us the hydronium ion plus a chlorine ion. Sulfuric acid plus water gives us hydronium ion plus a sulfate ion. Acetic acid plus the water gives us a hydronium ion plus the acetate ion. Okay? So we can write what we had up here like this, adding water to the acids, and that's what goes ahead and helps dissociate them. Now, let's take a look at some dissociation equations here. Recall that when an ionic compound dissociates or dissolves in water, it's no longer a compound. Instead, it exists as freely moving ions that are no longer associated with one another for the most part. And, with the exception of acids, molecular compounds do not dissociate. So, write the equation for dissolving solid magnesium chloride in water. Okay, so now what we're going to have to do is, first of all, write out the chemical formula for magnesium chloride. So that's going to be MgCl2, and it is a solid, and it's going to give us Mg2 plus Aq plus Cl minus Aq. Now, because of the 2 that's right there, it means that we need to also put a 2 in front of the chlorine ion right there. Okay? All right, moving on to the next one. Write the equation for dissolving solid aluminum sulfate in water. So aluminum sulfate would be AlSO4. The charge on SO4 is 2, so that becomes a 2. The charge on aluminum is 3, so this becomes a 3, which means we have to go ahead and put that in brackets. And this is a solid, and it's going to give us 2Al3 plus Aq plus 3SO4 2 minus Aq. Make sure you get all those charges and the coefficients and the states in your chemical equation. And we got one more on this page. Write the equation for dissolving liquid methanol in water. Okay, so that's going to be CH3OH, liquid, and when it dissolves, nothing happens because of the whole point right up here. Molecular compounds do not dissociate. So for that reason, methanol is still methanol, even though it's dissolved in water. Okay? All right, now let's take a look at some more acids and some more bases. Recall that acids are substances that increase the hydronium ion concentration. They are proton donors. So there's hydrochloric acid. If it was added to water, we would get chlorine plus hydronium ion. Nitric acid, same thing. We would get the nitrate ion and the hydronium ion. Okay. So when these are added to water, we get hydronium ions. Thus, they are acids. Okay. I need to fix a little bit of the wording there. So we'll say we get a formation of the hydronium ions. Thus, they are acids. Okay? Now, let's go to the idea of bases. Bases increase the hydroxide ion concentration, and they are proton acceptors. So, sodium hydroxide just dissolves into sodium and hydroxide. If you add water to ammonia, you get ammonium and hydroxide. So we see the formation of the hydroxide ion in both of those cases. So now let's talk about conjugate acids and bases. The way that Bronsted-Lowry base reaction goes, an acid plus a base gives us a conjugate acid plus a conjugate base. A conjugate acid is what remains after a base has been accepted or has accepted a proton, and the conjugate base is what remains after the acid has donated its proton. In any acid-base reaction, a conjugate acid and base pair are established. So when you add an acid and a base together, you are always going to get a conjugate acid with a conjugate base. Okay? When the acid donates a proton, the part of the acid left behind can accept a proton in the reverse reaction. When the base accepts its proton, the resulting molecule can donate that proton in the reverse reaction. So let's take another look at that reaction we looked at earlier when we react ammonia with water. Ammonia and water combines to give us the ammonium ion and the hydroxide ion. If we went in reverse, it would be the exact same thing, but the products would become reactants, and the reactants would become products. Ammonium plus hydroxide would give us water plus ammonia. So we can see that an acid results from the ammonia accepting a proton from water. The ammonium ion can donate a proton to the hydroxide ion. The hydroxide ion accepts the proton, making it a base. In the first reaction, ammonia is the base, and the ammonium ion would be the conjugate acid. And water would be the acid in the first reaction, and the hydroxide ion is its conjugate base. Now, ammonia and ammonium are called a conjugate acid-base pair, as are water and hydroxide. This is a reversible reaction, and it can be written as follows. We have ammonia as a base plus water, which serves as the acid, gives us the ammonium ion and the hydroxide ion. Ammonia is a base because it accepts the proton from water, and because water donates the proton, it is the acid. Okay? So, we're going to do an example here. Identify the acid, base, conjugate acid, and conjugate base in the following reversible reaction. Okay, so here's what we know. If we look at this reaction, we have hydrofluoric acid plus water. Then we get the hydronium ion and the fluorine ion. So if we want to look at this, we could say that this right here would be the acid. And because we get a hydronium ion, that would be a conjugate acid for sure. Now, an acid would only be able to be combined with a base, so that's the base. And the fluorine ion that's floating around by itself, well, that's going to be your conjugate base. Okay? Since water can act either as an acid or a base, it can either accept or donate the hydrogen ion. And just remember from our earlier in this unit, we talked about when we introduced the acids and bases once again. Substances that can act as acids or bases have a special name, and that name is amphoteric. And water is one example of an amphoteric substance.